and welcome to the proof of concept demonstration of the hardware for the evaluation or extraction of fetal heart rate as proposed by Fetalife. First, I want to show you the block level hardware which we have used for the extraction. The first one which you see here is a 5 volt DC power supply which we have used. It's a variable power supply. It's a DC power supply. We have also used a digital storage oscilloscope, a DSO, which helps you to extract the signal, view the signal, and store the signal. We do have a sensor here, which is HB100 sensor. This operates at 10.5 gigahertz operating frequency and at a 5 volt DC power supply. This is followed by the next block here, and this block is basically a preamplifier and a filtering block, and this helps you to filter unwanted signals which will be there within the fetal heart rate, especially the abdominal signal coming from the mother can be extracted from this preamplifier and filtering circuit. The preamplifier gain can also be adjusted depending upon the range at which the fetus is from the sensor. So it's a variable gain preamplifier design which is there on this heart block. We now come to the next block, which is basically a programmable AVR block, in which we have a 10-bit ADC followed by a Bluetooth module here, and this is supplied by a 5 volt supply in this case, and we also have an LCD display to detect the movement. Now this movement detection is via this HB100 sensor. This HB100 sensor works on the principles of Doppler shift, which means that whenever you have a motion across the sensor, there will be a relative motion between the sensor and the subject. Then there will be a phase change which will take place. The idea is to detect this phase change and say whether there is a light movement or a strong movement within the system. So this is the general scheme of thing which on the basis of the principle at which we are actually working on it. This low pass filter has got 80 hertz low pass filter, and we will be this module, or the sensor module, gives you a signal strength, output signal strength of approximately 100 to 200 microvolt, and that's the reason you require a preamplifier circuit to amplify the signal. Now we now therefore come to the ADC section here, and this is the overall section. Let me show you now the demonstration of the implementation of the POC. As you can see, this is the condition. If you can look at the oscilloscope, you will see that there is no waveform actually visible to you. And similarly, if you now come to the Bluetooth module through which we have connected to our the device, it shows light movement here detected. It shows a very light movement detected here, right? So this is in the condition when there is no movement or very light movement under the case. Obviously the threshold of movement can be shifted by using the gain of the preamplifier. Now let me show to you how we can achieve a higher gain by simulating the fetal heart rate change by my hand movement at this stage. So let me show you, please concentrate on the oscilloscope here, and you will actually see a movement taking place here. So this is the condition when you don't have any signal. There is no relative motion between the hand and the sensor, and as a result you can see the waveform is almost stable. There is no change. Now let me show you a change. Now as you can see here, now as I am moving my hand slowly towards the sensor, since the relative motion or the relative distance between the sensor and the hand changes, you would expect to see a change in the phase shift in the output waveform signal. As you can see, faster is my movement, more change in the phase is shown to you on the oscilloscope, right? So this is the basic criteria for the Doppler shift. The same information can be also sent to through a wireless module through a doctor to a doctor at a very far off place in a city, where he can actually take a call whether this patient needs to be intervened at this stage or not. To do that, we have a Bluetooth module, as I discussed with you in this case, and that is connected to through a programming onto our mobile device here. And as you can see here, it is considering a light movement detected, right? Is it okay? So we are detecting a light movement here, and you can see light movement detected. Let me show to you now, if there is a fetal movement, I would expect to see a strong movement. That's what I'm trying to see. You see, there's a strong movement which is visible to you here. If I move it here, I will expect to see a strong movement, and as you can see, the strong movement is coming here, and whenever the threshold crosses 3.5, there's a strong movement also seen here, right? And therefore I can detect a strong movement and short movement, right? The same things can be also seen at the LCD screen here, and as you can see the LCD screen, and if I move my hand here, the LCD screen shows a movement of 3.37. So we have set the threshold at approximately 3, and therefore anything above 3 is basically your strong movement, right? And this is what we are trying to do in this demonstrate in this POC. What we need to do through HACS is to go to the next level of modernization, or next level of hardware description, wherein these sensors will be integrated onto a wearable textile, and we need to do a sensor integration, as well as these electronics which is seen here, AVR as well as the preamplifier, need to be put on a single PCB for low power design applications. And we hope that the results are quite encouraging, because we have compared this with the FPGA board available to us.